And Shay is going to lead us towards the characterization of differentially private learning.
Okay, so first of all, I would like to thank the organizers and for inviting me here. It's my first privacy event, and yeah, it was a very instructive week, and I was happy to meet the faces behind the papers that helped an outsider like me understanding the definitions. And okay, so this is a joint work. I will talk about two joint works with Noga Alon, Olivier Bousquet, Roy Livni, and Moran Maliaris. And maybe it's interesting that, you know, Moran Maliaris, for instance, she's a logician, and Noga is, so none of these people is really like doing privacy as on a daily basis. Okay. So it's based on two papers, as I said. One is with Noga, Roy, and Ignorante, which shows that private pack learning implies finite Littlestone dimension. And the other paper, is with Olivier and Roy. And here actually we use differential privacy to study memorization in unsupervised learning, but we also have a corollary in the context of this paper. Okay, so let me tell you what the goal is. So this is a basic result in machine learning. It's called the fundamental theorem of pack learning, which is accumulated work by Vapnik and Chervonenkis from the 60s. And then in the West, the converse was proved by Blumer, Elmfeucht, Hausler, and Warmuth. And we will soon discuss each of these things, but it shows that uniform convergence is equivalent to proper learning, equivalent to not necessarily proper learning, and all of this is captured by some combinatorial parameter called the VC dimension. And our goal is to derive a private analog of these things. So basically, I just added the word private in front of each of the statistical properties. So private uniform convergence, I will tell you what it is later. Private proper learning and private learning. And our belief or conjecture or question, so that this is all captured by another combinatorial parameter, which is called the Littlestone dimension. And I hope that by the end of the talk, why do we conjecture it? So one obvious reason is because we have one direction, and we don't have any counterexamples for the other direction. But I hope that by the end of the talk, I will convince you that there are better reasons or other reasons to believe this conjecture. Okay. So first, I will tell you about the definitions of the 8 properties that we've seen. And then I will discuss the two directions that we know how to prove, namely the equivalence between private uniform convergence and private learning, and the fact that private learning implies finite Littlestone dimension. Okay, so let's begin with definitions. So for some of you, this should be known. So what is supervised learning about? So we assume that we have some domain X. X can be the real line, for instance. There is some known hypothesis class. So this is a bunch of functions from X to in the classification setting to 0 and 1. And there is some unknown distribution D on examples. So each example is a point from X and a label. And our algorithm is given a training set, which is drawn from this unknown distribution, and it outputs an hypothesis, namely a function from X to 0, 1. And the goal is to minimize the population loss. So I will soon tell you what it is, but the goal is that the output H will compete with the best hypothesis in class. Yeah?
What does less sim mean in this case?
So in the pack sense, like at most epsilon with high probability, we will get there. So So first of all, before what less than means, what does L of H mean? So we want to minimize the disagreement between H and the label on a random example. So this is an unknown, this population loss, the quantity we wish to minimize is unknown. What typically we use is the empirical loss, where we count on how many examples from the training set there is a disagreement. Yeah, so this thing means that with high probability it will be at most epsilon greater than that. So that's standard path learning or supervised learning. Now, what are these properties? Uniform convergence, proper learning, and learning. So as I said, the empirical loss is known, and the population loss is unknown. The difficulty in learning tasks is that you want to minimize an unknown population loss. The uniform convergence property gives us a universal way of doing it. It tells us that if we have enough samples from the unknown distribution, then with high probability, what we see is what we get. So the empirical losses of all hypotheses in the class are simultaneously close to the true losses, to the population losses. Okay, so it's a reduction from a learning problem to an optimization problem. Instead of worrying about an unknown loss function, we just need to minimize the known empirical loss. So of course, this implies learning, right? Because if we have this, then we can just minimize the empirical loss, and then with high probability, we will be close to optimum. Okay, so what is learning? So learning means that we have some algorithm A, such that if it sees enough samples from the unknown distribution, then the output will indeed compete with the best hypothesis in class. And proper learning is learning plus the requirement that the output always resides in the class. Okay? So these are standard definitions. And now, as I said, all of these properties, uniform convergence, proper learning, and learning are equivalent, as we will see, and they are all captured by a combinatorial parameter called the VC dimension. So the VC dimension is a property of the class H, and the VC dimension is the size of the maximal set that is shattered by H. And shattered mean, so x1 up to xd, domain points are shattered if we can see all possible dichotomies, all possible 2 to the d Boolean patterns on x1 to xd. An alternative and useful way for this talk to view that is that imagine a decision tree whose internal nodes are labeled by this x1 to xd, such that the ith level is labeled by xi. So I'm saying that, the observation is that the set x1 up to xd is shattered if and only if for every root to leaf path in the tree, there will be an hypothesis in H which realizes this path. Right? So for every H, there is some path that corresponds to it. So if h of x1 is 0, I go left, and otherwise I go right. And shattering means that for every root to leaf path, there will be some hypothesis in H that realizes this path. Okay, so we can think of the VC dimension as the maximum depth of a non-adaptive decision tree. Okay, non-adaptive means that all queries in every level has the same labels. Okay, so now let's go back to this fundamental theorem of path learning. So it tells us that for any class H, the following properties are equivalent. It has uniform convergence, if and only if it is properly learnable, if and only if it is learnable, and if and only if it has a finite VC dimension. Okay, and moreover, we have these bounds on how many examples should one draw in order to satisfy these properties. And this bound depends on the VC dimension. Okay. So, yes, so let's go to the private world. So the private definitions are really easy once we know the unprivate definitions, because we basically just add the word private wherever to the other definition. So what is private uniform convergence? So here I want a private mechanism A, such that if it is given as an input, a sample, which is large enough from the target distribution, then it will privately output another sample T. So T is a function of S, but T has to be private with respect to S. I want to protect the examples in S. And I still want the same guarantee to hold. What we see is what we get. So all the losses, the empirical losses with respect to T, are close to the true population losses. And again, of course, once we have such a mechanism, we can privately learn properly, because we just publish T, and then we apply any ERM, any empirical risk minimizer, which is not necessarily private. And post-processing will give us privacy for the composed algorithm. Okay, so is that clear? Because this is kind of maybe, so this is also related to sanitization and to synthetic data.
What's the difference between this and?
So sanitization, you usually want to, I mean, it's a special case of sanitization where what we want to publish is the losses of all hypotheses. I only care here about the losses. I think in sanitization you usually look at the.
So you don't have to be able to get to compute anything from the sample, just the losses properly.
Yes, that's enough to do ERM. So it's a special case of sanitization, but I call it private uniform convergence to. Yeah.
Is there a reason it has to output a sample? Could it not just output a measure?
So no, there's no reason, but it's equivalent, right? Because I don't worry here about computational efficiency. I just want to understand on a statistical.
The sample. It could just be any.
So once you have a measure, you can just sample from it enough samples, and then you get it. So it's just easier this way.
We don't care about computational complexity. Wouldn't it be simpler to just say you just specify L on every point in H?
Yeah, but I think the analogy with the uniform convergence it's equivalent. Maybe it's easier. Okay. Okay, so private learning, we just want a learning algorithm which is also private, as before, and private proper learning means that you want a learning algorithm which is also private and proper. Okay. What is the Littlestone dimension? So the Littlestone dimension is just an adaptive version of the VC dimension. So the Littlestone dimension is the maximum depth of a complete shattered tree. And now a tree is like before, but I allow different nodes on the same level to have different labels. Right, so I just want you to build me a decision tree as deep as possible, complete, such that for every leaf, there will be some hypothesis in the class which reaches this leaf. Okay, and the difference with VC dimension is that in the VC dimension, we just require that all nodes on the same level have the same label. So of course, in this way, in this adaptive way, we can shatter deeper trees. The Littlestone dimension can only be larger than the VC dimension. Okay. And an important comment is that this captures online learning. So just that, like the VC dimension replaces log class size in packed learning, the Littlestone dimension replaces log class size in online learning. And yeah, one thing that we learned in this work is that there seems to be a very deep connection between online learning and privacy. We will discuss it later. Okay, so as I said, like it's clear that the Littlestone dimension can only be larger than the VC dimension because adaptively you can shatter deeper trees. But it can in fact be arbitrarily larger. So the example is the thresholds. So you take all indicators of suffixes on the unit interval, all thresholds, And here you can see that, so the VC dimension is just 1. It's not hard to see. You cannot have 1, 0, 1, or even, yeah, you can, yeah, anyways. The VC dimension is constant. But the Littlestone dimension is very deep. You can shatter very deep trees, right? If you apply binary search, if your tree really does a binary search, like first acquire 0.5, and then quarter and 3/4, etc., then you can see that for every leaf, you can reach it with a threshold. Okay? So the Littlestone dimension of thresholds, although the VC dimension is just 1, Littlestone dimension is actually not finite, it's infinite. Okay, good. So this is our, as I said, this is our conjecture that in fact all of these, so again, the 3 statistical properties are equivalent, and the equivalence, we hope it will be captured by this Littlestone dimension. And of course, we would also like to get sample complexity bounds in a similar way. Okay, so this is the goal. This is the main message of this talk. And now let me tell you a little bit about what we know already, how to prove. So, yeah, so now we will discuss this assertion from private learning to finite Littlestone. Okay? So the theorem is that if H is learnable by an approximately differentially private algorithm, then it must have a finite Littlestone dimension. I'm going to discuss it very briefly, not. So this generalized result by Feldman and Shao, who proved it for pure differential privacy. And we also have quantitative bounds that the sample complexity should be at least, so we know that the sample complexity should grow to infinity with the Littlestone dimension, but the rate we get is very, very slow. It's log star of the Littlestone dimension. Okay. So let me just give you a quick overview of the proof and maybe mention some few interesting points, but don't worry, it's not going to be technical. Okay, so in the proof we prove the contrapositive. We show that if the Littlestone dimension is infinite, then you cannot privately learn it. Okay? And the first observation, which we'll discuss in the next slide, is that it suffices to show that thresholds are not privately learnable. And then we use a Ramsey argument, and I will discuss why Ramsey is sort of necessary in this context. But, okay. So why is it enough to show that thresholds are not privately learnable? So here's the definition. So here's the important definition. So a class contains k thresholds. How do we make it not really jumps? Okay, so a class H, we say that an abstract class H contains k thresholds if there are k concepts and k points, k hypotheses and k points, such that if you look at the metrics that they induce, it's a threshold matrix. It's a triangular matrix. And the statement is that if the Littlestone dimension is infinite, then you contain infinitely many thresholds. So if I give you any class with infinite threshold dimensions, Littlestone dimension, then you can find in it thresholds embedded. And therefore it's enough to show that this part is already hard for private learning. And there are also quantitative bounds by Saharon, Shelah, and Hodges from model theory that, you know, if the Littlestone dimension is at least D, then you could contain at least log D thresholds, and vice versa. And let me just mention that this is an open, like whether it's tight, the quantitative bound is open. And I think it's a nice question in combinatorics. Good. So this is why it's enough to consider thresholds, because any Littlestone class, any class with infinite Littlestone dimension must contain thresholds in it. So, okay. And yeah, so we showed that thresholds cannot be learned privately. And we do it via a Ramsey argument. And let me try to convince you why Ramsey is useful in this context and maybe also in other contexts that arise in private learning. Oh, man.
It's not your fault and it's not deterministic.
Sorry?
It's not your fault and it's not deterministic.
Yeah, I know this.
Play automatically within the PowerPoint. Like a feature that's called play automatically. I'm not sure I know how to turn it off, but there is.
Okay.
mode.
We want to on that or something.
Okay.
But it kind of happened spontaneously.
The
The talks that
slideshow
I've done before. without
option
it.
where you-
No, because it's recorded your previous time.
Why? Who told it to?
You told it by mistake.
Okay, let's continue. So again, I think in this slide maybe there is in this slide there is an interesting maybe a take-home message that I want to tell you about. Okay, so why are lower bounds for private learning more challenging? So in typical sample complexity lower bounds, and not only sample complexity, in many lower bounds, we use a minimax argument. So it's enough to show one distribution which is hard for all algorithms. Okay, this is something that, this is a recurring phenomenon in computer science. So even if the algorithm knows the distribution, it cannot utilize it, it cannot exploit it to achieve better, to break the lower bound. So for example, in standard park learning, we take a distribution over a sharded set. And this is the lower bound against every algorithm, even if it knows the distribution. In private learning, it's different. Once you know the marginal distribution, you can construct a finite class, an epsilon net of the class, which is relatively small, and use it to privately learn the class. So once the distribution is known, every VC class is privately learnable. So we need some sort of mechanism that, given an algorithm, outputs a hard distribution for this algorithm. And this mechanism, or such mechanisms, naturally arise with Ramsey arguments. Because Ramsey, for those of you who know, you showed that for every coloring of subsets, there is a large monochromatic set. So the algorithm somehow defines the coloring, and the monochromatic set, which is obtained by Ramsey, gives you the hard distribution. And yeah, I think so. So I think this is useful in these settings where you don't have this. So once you know the distribution, things become easy. I already have two recent examples of the same idea. Okay. Now let me tell you something about maybe an open question here in this context. So what we showed is that private learning implies finite Littlestone dimension. And what I told you before is that finite Littlestone dimension is in fact equivalent to online learning. Come on. Okay. So as a corollary, we get that private learning implies online learning. Namely, any private learner I give you, there is a way to transform it to an online learner for the same class. Okay? But this is not the story that the proof tells you. The proof is lower bound. It tells you the contrapositive story. It would be very nice, I think, to find a constructive proof in the sense that it gives you a way of transforming a private learner to an online learner. Okay, I think this would be more intuitive also. And of course, once you have this point of view, you can also extend it to continuous setting, to other loss functions, etc.
Just a point, I'm not sure how it connects to the technical content here, but these types of transformations are known for like some specific problems.
I know.
So,
Yeah, but
it's not crazy to think that
yeah, and this also supports this intuition that we think that online learning and private learning are related, and this Littlestone idea is not just because that's what we know how to prove.
So already in this non-constructive, even in this non-constructive argument, you're losing the sample complexity. You're going from
That's true.
dimension to the log star. So
That's true. That's true. So this shows you
so I'm just saying that even if it was constructive, you would be blowing up things by whatever.
Yes, yes, that's true. But still,
So maybe for constant dimension, you would.
even there we don't know yet.
So you're saying that you want to be able to take a private learner that does not have any online aspect of it at all and turn it into an online learner?
Yes, maybe use it as a black box in an online learning algorithm. Like, it's like follow the leader, be the leader kind of things.
I mean, there are connections, right? There's this adaptive data analysis, generalization stuff that. No, maybe there's a connection.
Okay. Okay, so let's continue to the last part of the talk, which is the connection between private learning and private uniform convergence. And here you will see, I hope, that again, online learning or Littlestone Dimension really makes sense. Okay, so now we prove that if I give you, so it's clear that if I give you a private uniform convergence mechanism, you can get from it a private learner, a proper private learner. Right? You just apply this mechanism and apply any ERM later on the published sample. What we'll show you is how to take a private proper learner and transform it to a mechanism that does this private sanitization of all losses, private uniform convergence. Okay? So, I just remind you that uniform convergence is what you see is what you get, and private uniform convergence means that we can publish sample T privately with the same losses like the population losses. Okay, so the theorem is that H is privately properly learnable if and only if it satisfies the private uniform convergence property. Okay. So as I said, one direction is trivial. If we have a private uniform convergence, we can utilize it to learn privately. So we estimate all losses in a private manner, and then we just pick the hypothesis with the minimum loss. Okay. Good. The other direction is more difficult. I give you a private proper learner, so it can minimize. It can find an hypothesis with a minimal loss privately. But now I want to publish all losses of all hypotheses. Okay? So what we will use is that this private proper learner gives us a finite Littlestone dimension, and in particular this gives us an online learner. This will be crucial. So how can online learning help? Okay, is this clear? So how are we going to build now this private uniform convergence mechanism from the proper learning? So the idea is to use an adaptive algorithm. So our algorithm will have the following structure. We can think of it as a game between Alice and Bob. So Bob will hold a sufficiently... So Bob will hold a sufficiently large sample from the target distribution, and Alice will not know this sample that Bob holds. Her goal will be to find T, to output T in a private manner that will be indistinguishable from S. So, so Bob holds a sufficiently large sample. S is not known to Alice. Alice's goal is to find T, which is alpha similar to S. So the losses between S and T are approximately the same. Cannot do it. Okay, and the way it works is that in round I, Alice will send Bob a candidate Ti. Bob will check if Ti is alpha similar. If it is, then he tells her we are done, output ti. Otherwise, Bob will send Alice a counterexample, namely a name of an hypothesis for which the two differ. Okay? And now the observation is that if we can make Bob differentially private, then this whole thing, the composition, will be a differentially private algorithm.
So how is this like an online learning?
This is a sequential process, and we will analyze it using the Littlestone Dimension and its connection to online learning.
You just think of any message of it as like T examples, and then you look at the online learner, or?
So we think of this game as an online learning game. You can reduce it to online classification.
Okay, yeah.
But the connection to online learning is the sequential nature of the algorithm. Alice sends a candidate, Bob checks if she's done. If yes, lets her know, otherwise sends a counterexample. Okay, go to the next slide, hopefully it works. Yeah, so the proof overview is pretty simple. So differentially private Bob. So it's enough to show that we can make Bob differentially private and that we can bound the number of examples. Okay, and we get it. Why do we get it? Because if H is privately learnable, this gives us pretty automatically a differentially private Bob. There's a little calculation, but it's easy. And so we can make Bob differentially private. That's the easy part. Now we want also to get a bound. We want to show that Alice can win in a small number of rounds, and this will follow from the finite Littlestone dimension property. So since H is privately learnable, there is a finite Littlestone dimension, and then there is an argument which maybe also conceals your confusion about the connection, because this is a little bit technical, but you can show that finite Littlestone dimension, even in this setting, implies a bound on the number of rounds Alice needs. Okay. So yeah, so let me summarize. So the way we want to take a private learner, convert it to a uniform convergence, the way we do it is we say that private learning implies private plus online learning, and together the two imply private uniform convergence. And the uniform convergence complexity will be roughly the number of rounds times the private complexity, the number of samples, Alice needs. And this gives you indeed a connection between online and private learning. So notice that we proved an equivalence between two statistical properties, private uniform convergence, sanitization, and private learning. There is no Littlestone dimension, there is nothing there. It's like to define these properties, you just need the language of probability theory. You don't need combinatorics or nothing like that. But still, the proof heavily utilizes this sequential semantic of Littlestone dimension. And I think this suggests that indeed there is a deeper connection. And our conjecture is not just because this is the lower bound, the best lower bound we could find, but maybe there is something deeper, a deeper connection between these properties. Yes?
So the way I normally think about these, like synthetic data generation problems, as you described, there's an interaction between Alice and Bob, like, okay, so Bob needs a differentially private learner, and the way I'm used to thinking about it, what Alice needs is a no-regret algorithm, not for H, but for sort of like a dual class to H, where the role of the data player, where the role of the data and the hypotheses are swapped.
Yes.
And so I guess like, so can you say a little more about this technical part? Because I guess finite Littlestone dimension implies a no-regret learning algorithm for H. Does it also imply a no-regret learning algorithm for this dual class?
Yeah, so first of all, yes. And again, here we use results from model theory.
Okay.
So it turns out that if a class has a finite Littlestone dimension, then also the dual class will have a finite one.
Okay, that's a useful fact that I didn't know.
How finite?
Again, we don't know because it depends on this connection with thresholds. So it's we don't know exactly type, but
Is it exponential?
it's at most 2 to the 2 to the d.
It's not a tower.
No, it's not a tower. It's small. Yeah, but I mean, this shows you that there are.
Okay.
But let me just mention that this is not even enough in our setting because, like, the technical part is actually not this part because this is, it's a corollary of a previous result. The problem is that the online learner you get from just having a finite Littlestone dimension is not necessarily proper. Because you see, in this game, we really restrict Alice to always send Bob distributions or like samples that encode uniform empirical distributions. And this is an extra constraint. Like if she could send any loss assignments to the hypothesis that can be negative, or then it would be easier. But the fact that it's non-proper, this really complicates things dramatically.
Okay, and like if you had a non-proper learner, it would still work out if Alice had a no-regret learner for the larger class that Bob was using, but that might not be implied by the finite Littlestone dimension.
No, I mean, it doesn't really translate, like non-proper learning in the online setting does not translate to a bigger proper learning in the classification setting. It's just a different object. It's like instead of working with distributions, you work with pseudo distributions or with signed measures. So you can think of it that Alice in each round sends a distribution. This distribution should be indistinguishable from the distribution Bob holds. If Alice could send signed measures, like it also have negative numbers, or even more than that we actually need, then it would be a corollary of the Littlestone thing. But since you really restrict Alice to send distributions that are encoded by a finite sample, it complicates the proof, and there is a minimax argument, and yeah, the reason I insist on saying that is because we just have reviews from Colt, and they said, yeah, this is trivial, like this part is trivial, and so it all follows, and actually, you know, it worked pretty hard. Too bad. Okay. Yeah, so basically I'm done. Yeah, so fill in the blanks.
Any further questions? We grilled Shay pretty thoroughly.
Is this just a question? I didn't entirely follow the last part you said, and that's fine because it's online. But is that sort of discussion in the paper, and was it like ignoring?
So there are two papers here. It is discussed in this paper.
Is there a good, it is good. I was just saying, like, is there a place I can go? Like,
it is discussed in this paper, which actually is not on this topic. As I said, there we actually use differential privacy to study memorization in unsupervised learning. But as a corollary, we observe this.
Is that paper available?
Yeah, on my archive, and hopefully it will be accepted to quote.
So it's not really a question, but so Mark, John, and I have a paper where we did showed some separation between private, online, and offline query answering, which is not quite the same as learning. Just kind of wondering whether that would lead to some separation, because I think you were suggesting about connecting private learning to online learning.
Like in the adaptive data analysis context, you mean?
Those
Query
are different
answering?
paper. It's just private, online, and offline.
So what kind of result do you like?
We had like an exponential separation. I can't remember the exact result. Maybe my courses are here. Breaking about the
the context is like whether or not you're asked to answer lots of questions, and the question is, do you get to see all the questions right away and then think about what to do, or do the questions come? Do you have to produce answers as the questions come?
Right.
So it's like not
And there was
obvious,
it's
right?
yeah.
How the connection comes.
But when you mentioned connecting private learning to online learning, that kind of reminded me of that.
Yeah, sounds interesting. I would.
Okay. If there are no more questions, thanks for having me.